All right, thanks for the introduction, Bill. It's really interesting to see that quite a lot of you are already using Service Mesh or have given Service Mesh a try. So hopefully I'm not going to be telling you too many things that you already know, or perhaps you're going to be able to help me answer the difficult questions that I'm sure are going to come up later. So this is a kind of abbreviated version of the talk that I gave at KubeCon around a guided tour of Cilium Service Mesh. And really I wanted to talk a little bit about how we got to where we are with a sidecarless service mesh. I think a lot of people are aware that with Cilium Service Mesh, we have this model that avoids having a sidecar proxy injected into every pod. I wanted to talk a little bit about how we arrived at that situation and why we believe that's a really good approach. So if we think back to before service meshes really were a thing, before we had this idea of sidecars, we would have application-specific code that fulfills the functions of a service mesh. So for example, in our application, we might have code that implements retries or that requires mutual TLS, mutually authenticated secure connections. And that code would be language specific. We'd probably use libraries, we might use Go libraries or Python libraries or Ruby libraries or whatever application language we're using to implement these features like MTLS and what have you. And that would mean a language specific library for every language that's being used, probably writing extra code in every application. And some bright people, probably several bright people, thought, well, it would be a really good idea if we didn't have to keep doing this for every application. So the idea of a sidecar, and specifically for a service mesh, a sidecar proxy came along. So with the sidecar model, we inject a container into every pod, and that can implement this service mesh features. We also use sidecars for other kinds of tooling like security, observability tooling. A lot of that is implemented with the same kind of sidecar injection. And by implementing the sidecar container into a pod, that sidecar can get access to the application, it can intercept network connections, and so on. So that has a great advantage in terms of the application not needing to implement this functionality. It doesn't even need to be aware that the sidecar exists. We can write our application without needing to worry about service mesh features. But this is probably not the end goal that we need to reach. Why can't we implement that service mesh functionality as if it were part of the network stack? If we think about the history of networking in Linux, TCP/IP didn't, used to be part of the kernel. You used to have to implement your TCP stack within your application. Over time, that's moved into the kernel. It's where we expect that networking functionality to be. Does it make sense in a distributed environment like Kubernetes to expect to push service mesh functionality also into the kernel? Can we implement this today? Well, a lot of this is there, but a layer 7 functionality isn't implemented in the kernel yet. But maybe some of that we can implement in eBPF and essentially extend the kernel to provide that functionality. Now, I think one of the interesting things about Cilium is that we already have layer 7 network policies. We have visibility. All those of you who tick the box about using Hubble, you'll be aware that you can see application layer information in the network flows. You can see HTTP requests or gRPC requests being decoded in Hubble's observability flows. So that kind of leads us to thinking, could we do more of the other layer 7 functionality that's required in a service mesh as part of Cilium. We think about how Cilium works prior to service mesh. We have one Cilium agent running on every node, and that agent is responsible for injecting eBPF programs into the kernel for different endpoints and for different connections that are happening. Those eBPF programs are being created dynamically. And we also have an Envoy proxy built into the Cilium agent, and we're using that for layer 7 functionality already. So we already have this situation with Cilium agent and one Envoy proxy essentially running in the node. So the question is going to be raised, can we use that Envoy proxy for service mesh capabilities? Let's think what a service mesh is. The number one feature that people talk about when we've asked them, when we've sent out surveys about service mesh, the number one thing that everybody wants is really great observability at layer 7. Ingress is a hugely important part of service mesh. We need to be able to connect requests from the outside world and load balance them into the backend services. And that may require some protocol passing so that we can route different requests to different backends. We might have certain rules that we need to apply based on the URL. We have layer 7 traffic management, which I think is very strongly associated with service mesh. The idea of load balancing our traffic across different backend pods, perhaps with rules that control how we're going to balance between different versions of a deployment, and with rules around how we're going to do things like retry requests if there's a failure. And a very strongly desired feature in service mesh is to be able to secure the connections between services or between an ingress and backend. And that's or that security is based on Kubernetes identities. And if we look at that list, a lot of that was already implemented in Cilium as a CNI. We already had layer 7 observability. We already had load balancing. Cilium acting as a key proxy replacement is load balancing requests to different backend pods. We already had protocol passing that we were using Envoy to fulfill. We already have knowledge of identities. We have knowledge of Kubernetes identities, and we enforce network policy security based on that. We don't have MTLS on this list, but we do have some security features that relate to Kubernetes identities. So I remember when I first joined Isovalent, and Thomas had said to me, yeah, Cilium is already an 80% service mesh. And I think that was absolutely true. What do we need to do to fulfill the other 20%? Well, one part of that is adding or using more of the capabilities of Envoy. So we already have that Envoy agent, that Envoy proxy in the agent. With service mesh, we are adding the ability to program individual Envoy listeners to perform this kind of traffic management and ingress rules. So that gives us a huge step forward towards being able to implement a service mesh. So I'm going to show Ingress and how Kubernetes Ingress in using the Cilium Service Mesh creates an underlying configuration for an Envoy listener using this Cilium Envoy config CRD. So I hope this is going to be big enough to see. Somebody shout if it looks too small. I'm going to run Hubble to observe what's happening in my far, far away namespace. At the moment, there's nothing really going on. And I have a few pods in this namespace. So I have a Death Star, and I have a TIE Fighter and an X-Wing. And okay, I'm going to ignore those. I think those are some kind of Hubble relay error. I saw that earlier when I was setting up the demo. I don't think it's going to damage things. Now, I also have an Ingress set up for the Death Star. So that means I should be able to route traffic to the Death Star using this load balancer address that Amazon has given me. So what does that map to in terms of services? So my Death Star, my two Death Star pods are forming, they're sitting behind a Death Star service on the cluster. But I also have this load balancer service, Cilium Ingress Death Star Ingress, that was automatically created when I created the Death Star Ingress. I didn't do that live because it can take a minute or so for EKS to set, or for AWS to set up that Ingress, or to set up that load balancer rather. But that's been automatically created. And the other thing I also have is a Cilium Envoy config. So I've just used the abbreviation for Cilium Envoy config, and we can take a look at this. Oh, need to actually specify that it's a CEC. And this should tell us about the configuration that's been automatically created based on my Ingress definition, which I'll show in a moment. So we can see, we'll ignore the metadata fields, the spec here, the backend service is Death Star in a namespace far, far away. And it's created some Envoy configuration that matches on this v1 request landing URL prefix. And when it receives requests to that prefix, it's going to route them to, it says cluster, this is Envoy nomenclature, but this really in our world means a service. So let's compare that to the Ingress, which is called Death Star Ingress. So this is all that I had to configure. I configured an Ingress that routes for any host to, using this path, it will route to my Death Star service. Creating that Ingress, configuring that Ingress kind of manually or with some YAML resulted in the creation of the Cilium Envoy config and the load balancer. So what that means is I can make curl requests. Oh, I'm going to need that address, aren't I? So I can make curl requests to this address. And if I'm just going to not specify the full prefix. So this is not one of the routes that I have configured in the Ingress. And that came back as 404 not found because there is no known route programmed in for that, to the Ingress for that route, for that path. But if I specify that I want to request landing on the Death Star, it's going to tell me I have to post. And we can also see at this point, the traffic is actually being routed within the namespace. So we can see the request here and the response coming back, which is a 405 because it's the wrong kind of request. So if I change this to a post, don't think I need the V anymore. And that successfully landed. So I was able to use the Ingress to route traffic to the Death Star backend successfully. So I hope that showed how Ingress creates these underlying configurations and how that's programming the Envoy configuration on the node. Now, that configuration is accessible. You could create your own CRDs, your own instances of the Cilium Envoy config, but it's quite complex. We automatically created one based on Ingress, and the future direction of Service Mesh is that we could create Cilium Envoy configurations automatically based on what's configured at a higher level in abstraction. So Ingress is the first example of this integration, but we could expect to make similar integrations with the Gateway API or the SMI interface, Istio, Linkerd configurations. These could all be mapped to those Cilium Envoy configs. And this is going to be community driven. This is going to be driven by requests from customers. Deciding which integrations to build is very much dependent on what our users are asking for. And for Isovalent as a company, we're interested in what our customers want to integrate with. So this is the future direction of making Cilium Service Mesh accessible and configurable. And we know that from our surveys, we know that people are very interested in Cilium Service Mesh because of the reduced complexity, because of avoiding sidecars, and the fact that that allows us to save resources, reduces the operational administrative complexity, gives us much better performance. And we've published some performance numbers on our blog. And also it allows users to avoid the kind of race conditions that can happen within a pod when you've got numerous containers that need to start, and they may need to start in a certain, or things may need to happen in a certain order, and there can be race conditions for certain applications. So the resource usage becomes improved because we only need one instance of the Service Mesh proxy per node rather than one instance for every pod. The network path in a sidecar model is really quite convoluted. We have to, within the pod, a packet has to traverse the pod's network namespace essentially 3 times so that a packet can come out of the application, get routed through the proxy, and then back out of the pod onto the host, where it then needs to go through the host network stack in a traditional networking environment. But if we're using eBPF, we can route those packets through the eBPF fabric, and where necessary, route into the Service Mesh proxy on the host as needed. So I've got a couple of slides of some of the performance measurements that I mentioned. I mean, we see latency sort of roughly halved, which is kind of what you'd expect because of the route that packets need to take. Throughput performance is very similar, slightly better, but very similar. And I think probably the most striking difference is that pods become ready much, much more quickly because they don't have to wait for sidecar proxies to be ready as well as the application pod. That's made a significant difference in the tests that we've run, and we'd love to hear what you've been seeing in terms of performance as well. The last piece of the puzzle that we don't have today is mutual authentication, mutual TLS. And the future direction for this, Thomas wrote a very good blog post that outlines this. The idea is to separate the cryptographic authentication of services, which will be done in user space, from the network layer encryption. So we can take advantage of encryption within the kernel, which is way more performant, but provide the certificates into that encryption from, it could be Spiffy, it could be Cert Manager, whatever certificate management tools, again, that the community and that our customers are most interested in using. So watch this space for the development of this next generation encrypted connections. I think this is going to be a very exciting development. It's going to be very exciting to see how this improves performance and how it allows us to be flexible with the management of identities and certificates. So to sum up, Cilium Service Mesh is using eBPF to give us the best possible data path that we can achieve, falling back to the Envoy proxy when it's needed for layer 7 termination. And that eBPF capability gives us essentially native networking performance and much more improved latency because the network path is much shorter. And it can support any kind of network traffic. The control plane, the configuration will really be driven by the integrations that are demanded by the community. And observability. We already have amazing observability built into Cilium through Hubble project and now also through Tetragon, which Natalia will be talking about shortly. But access into network flow data at layer 3, 4 and also at layer 7 can be exported into Prometheus or logging, amazing Grafana dashboards that we can configure and that are continually being expanded, and also exporting that kind of network flow information to SIMs and logging systems. So that is pretty much what I was going to share in terms of Service Mesh. I slightly over time, so I hope I've got time to answer a couple of questions. I did see Zoom saying that there was a raised hand. So, and there's a couple of good blog posts, if you haven't already read them, on the Isovalent blog that will give you more detail about Cilium Service Mesh. Okay.
Yeah, so the first question is, what metrics are exposed by Cilium Service Mesh? Is there any way you can visualize the flows?
Yeah, so essentially we are exporting the same kind of metrics in Service Mesh as we're exporting in Cilium just as a CNI. So the let's say observation points that we're looking at in the kernel are the same. And so we can visualize flows using Hubble. We get the same metrics. I mentioned the Grafana dashboards. There's a very rich set of metrics being exported. Yeah, so at layer 3, 4 and at layer 7, a huge variety of metrics, whether that's to do with packets being dropped, the protocol type, the latency, throughput, all these metrics are available. I also see, I saw in the Q&A, Bill, there's some questions from Rio that are pretty interesting, and I want to jump to those. Yeah, so Rio's asking about whether the layer 7 type processing will ever be done in eBPF, which I think is a really fascinating question, because we've heard a few people talking about eBPF not being Turing complete. And well, it's not strictly Turing complete, but and it's not strictly Turing complete because there is a limit on the number of instructions that can be handled by an eBPF program. But that limit has been increasing over the evolution of multiple kernel versions. And it's also kind of artificially extended using the tail calls. So the practical limits on what you can do in eBPF programs are pretty reduced. I've also seen people saying that, well, we can't really hold state in eBPF. Well, yes, you can. That we have maps to hold state. So today we do have, I know that at least internally, I'm not sure if this is public, but at least internally we've done HTTP2 protocol parsing in eBPF. I don't think there's a theoretical reason why this couldn't be done in the future. I don't think it's going to be done, in a matter of days or weeks, but I do think it's at least theoretically possible. But it's not trivial. There's a lot of work there to implement the layer 7 functionality, everything that Envoy is doing. I mean, Envoy, I don't know how many thousands and thousands of lines of code it is, but re-implementing that in eBPF would be, a significant amount of work. I think eventually, yes, it probably will end up there. And I think we'll increasingly see parts of that processing moving to eBPF where there's kind of low-hanging fruit from a performance point of view. But I don't think we're going to see the end of user space proxies, certainly not this year. I hope that answers that question.
I guess related, I think you answered a little bit, but maybe if you want to expand on it, if so, what's currently blocking it?
Yeah, I mean, I think blocking it is really the work, the typing it in, and it's going to be a bunch of programming. So and whether or not it's necessary, whether or not the performance, I mean, I think eventually, much in the same way that probably 20 years ago, 30 years ago, I don't know how long ago, people were probably going, is it worth putting TCP in the kernel? That and that's not even a question now. So yeah, I think it's just work, I believe.